Hey everybody, welcome back to Fastware. Thanks for tuning in to today's video. And today we'll be looking at the cost of thread synchronization, which I think is a pretty important topic as threads become more and more popular. Now, most of the applications are multi-threaded. The real cost of threading and synchronization of threads is sometimes lost on people. Because they just say, oh, we can just scale with multiple threads and it's going to be easy as that. So threads obviously provide a lot of challenges when you program. Not to mention, you have deadlocks, leaf locks, problems like that. But even if it's done well and correctly, there's still costs associated with it. And that is to do with how we synchronize our threads, so the data which is accessed by these threads, right? Now, C++ provides several methods for us. So the common ones are the mutexes. There are also semaphores and other stuff that you could use, but mutexes are sort of the bread and butter of any programmer which touches threads to use. Then you have a little sharper tool, which we have atomics, right? And I will be looking at a bit of how we use atomics as well. Now, the last two are sort of not particularly, I would say, a synchronization methods, but it's a form of synchronization. So let's dive in and have a look at how they are implemented and then follow up with a cost that associate. So normally what you would have is you have a mutex. Here's the data that you want to protect. It has the min, max, and account. And the way we use it is normally we would use something like log guard or scope guard or whatever it is. And then you basically construct your log guard by passing the mutex as an argument to the constructor. And then anything within this scope will be basically synchronized. And what does it mean to be synchronized? That means that reads and writes cannot be reordered on the assembly level or the micro op level at the CPU across this scope. So that means you cannot basically put in, you can basically move reads into the scope, but you cannot move basically writes out of the scope, or you cannot put in additional writes here. So this scope is basically protected from any other instructions that happen across it. So this is what synchronization basically means using a mutex. So reads and writes cannot be reordered pretty much on the memory subsystem level, right? So that's how we protect it. Now, the atomics are a little different, so the same sort of a data structure, but now we don't have a mutex. Each of our variables are atomic, so you have a minimum, the maximum, and the count. So our implementation looks slightly different. It's a bit more involved, I would say. So maybe that's why people don't reach it. So here don't use sequential consistency, but instead I use relaxed atomics. So relaxed atomics, if done well, can provide more performance for you, especially on some of the systems which are not x86 sort of a ARM specifically. They have a very different synchronization mechanism on a CPU level. So this is how you would basically implement such a pattern, like the checking. So we first read our value from our max. We compare if value is larger than the current max, and then we want to store into our max. But what we want to do is say compare exchange. So compare exchange, as a first argument, you provide a current expected value to be stored in a max. So this max, we say the same value that was there before, and we want to replace it. So this is the new value that we want to replace that value with this value. And the memory orders acquire release. So it means that we will be acquiring the value of max, and then when we store it, we want to do a release. So just saying store this value so it will be available for the next thread as it comes in. Now, this negation stands for basically compare exchange weak can fail spuriously, so it has to be done in a loop, saying basically that the if this operation fails, the new max value, which is in here, if those two do not match, will be, because this is a reference, so if you look at here, so the first argument is a reference, the second is a value type, an L value. Therefore, if this check will fail, so it'll provide false, the new max value will be populated, so then this comparison will happen again, and it will try to store it again if both of these conditions are met. So you basically loop and keep updating max until either this condition fails or you store a new value. The minimum done in exactly the same way. And here we have our count. So for our count, we're using fetch add, which is just we want to increment it by 1, and we want to do it in a relaxed manner, meaning no matter how you're gonna store this, eventually we want to reach to the maximum count. So on memory subsystem, it can be stored in individual threads local store, and then later synchronized together. So, but the particular implementation, how it's done on the CPU, is kind of a CPU specific, so we're not going to be talking about it too much. But relax basically says, eventually I want it to be consistent. I don't care that it's now consistent, right? So that's pretty much it for the atomics. So the no sync implementation that I have here relies on the fact that we can basically have an array of data, which is the same size as number of threads we have, and then each thread basically indexes into our store to access its own individual data. So therefore, we're saying we don't have to synchronize across different threads. We just write into individual data and then synchronize it once, for instance, the threads have completed their work, or at some points, you know, like you can introduce individual writes, and then some event comes in, wants information, we can then grab a basically maybe a lock of some kind and then synchronize it this way, or just copy these values out and avoid synchronization altogether. So there is ways to avoid it. It's not always possible, I want to mention, so there's a caveat obviously, but if it is possible, you can approach your synchronization in this manner. However, this particular implementation, no sync, has a problem. And that's to do with the, again, how synchronization works on the CPU level. So I'm going to be diving a little bit into hardware synchronization techniques here, to explain a particular problem. It's called false sharing. So read and writes on a CPU level in a memory, it's not done at the word level, like 4 bytes of this integer, right? It's done on a cache line size, so 64 bytes. So now we can evaluate our data structure, which is 12 bytes, right? And therefore, in a vector, these are going to be placed one after another in a sequential manner. So there will be more than one of these data structures inside the same cache line. So now if one thread wants to, let's say, access the first one, it will read that cache line and then try to write to it. But because you write the entire cache line, you have a problem when a second thread needs to, for instance, access the second value. And therefore, now you have a issue with this data basically having to be migrated from first cache to the second cache, to second thread's cache, and then back to the first one. So this bouncing of data from one CPU cache to, well, one core's cache to the other core's cache is called false sharing. and it can actually lead to severe performance degradation in your system if not accounted for. So I would definitely recommend you to read up on how this actually occurs. Maybe I didn't explain it that well, but there's tons of material on this, and I would recommend really looking into that. However, I have a different implementation here. It's called benchmark no sync with alignment. So understanding that this can occur, this fault sharing can occur, what we want to do is basically say, okay, so dumb, simple thing to do is just align my data structure to 64 byte bound cache kind of a alignment, right? And therefore, the entire cache line will be occupied by this one structure. So obviously very wasteful, but it can be done. So what this does is basically saying that this data store now will be aligning a lot more data. So let's say in 8 threads, so 8 times 64 bytes rather than 8 times 12 bytes. So there will be a lot more waste. However, there is a benefit. Now, each data store is stored in individual cache lines. Therefore, the fault sharing cannot occur, as individual threads, as they're going to be accessing, they will be acquiring their own individual cache lines, and they're not going to be shared across multiple threads, right? So the code looks exactly the same apart from this align as, which is I think C++11 metric. If you're using C or something else, you can always do padding, which is usually done by using, for instance, byte, which is basically char padding, and then, for instance, so 12, and then so this would be 48 bytes of padding, right? And you can accomplish exactly the same thing. And if you look at any high performance code, let's say Linux kernel, you will find a bunch of these that they want to align to very specific sizes in order to facilitate things like that. So we looked at how these things are implemented, and then basically once all the running and summing is finished, it basically accumulates at the end to have the result. So let's run our little benchmark here. So my methodology for benchmarking this is, of course, we have data sets of different sizes from 100 to 100,000, and we basically will run for one thread to see a single threaded performance. So when there's no contention for multiple threads, then we have 2 threads, which is basically a weak contention, and then we have 4 and then 8 threads at each scale for each different benchmark. And then we can basically quickly scan through this data. So here thread 1 is 470 nanoseconds. This is 250, so it's about 2 times faster. Okay, so Atomics is about 2 times faster than Mutexes in this particular case. The no sync, oh, look at that. It's about 70, which is about 3 with a bit times faster than using Atomics. And then obviously at single threaded performance, as you can see, the data structures with alignment are a little slower. Now, why that is? Obviously, it's simple to understand, right? Because now at a single threaded, all the data is packed closely if you have only 12 bytes of, for each structure. And therefore, single cache line contains multiple of these, so the CPU doesn't need to fetch any other cache lines in order to index into these. So the performance is much better here. Now, when you have each data structure padded and aligned to 64 byte cache boundary, you're basically wasting a lot of space. So now, in order to access another basically value there, another data store, you have to jump quite a bit, and therefore this padding actually incurs actually space and time penalty here. However, if we just look at 2 threads now, so 2 threads, so it's weak contention, so we have 8,500 nanoseconds, and atomics is only about 1,000. So it's 8.5 times performance improvement versus the Mutex. The no sync is about 230 nanoseconds. So you see how false sharing starting to protrude its ugly head here and kind of cost us problems by slowing this implementation down. While actually the no sync with alignment has exactly the same performance. 90 nanoseconds. That's it. Nothing complicated here. And it's about 3 times faster, right? And when we go to all the way to 8 threads, so we still have about 19 nanoseconds, while the not padded synchronization is now about 4 times slower. Atomics are about 9 microseconds, and mutexes are all the way at 38, 39 microseconds. So it's becoming quite slow because the contention is quite severe. And the atomics, the relaxed atomics, are designed for lock-free programming. So if you know how to use them, or if you don't, practice and use them in your projects, so you can, as you can see, gain quite a lot of performance here. So I have a few charts to share with you. So this is how the scaling looks. The numbers themselves are not particularly interesting, but the important thing is, so this is from light to dark. This is from 1 thread to 8 threads, and you can see the scaling for the atomics, exactly the same thing. And then here is our no sync in red, and then in purple we have no sync with alignment. So you can see how flat these are across these different dataset sizes and across different amounts of threads. So we can dive into assembly, but there's nothing particularly interesting to look at the assembly, because it's just a couple of integers that we actually work on. So I'm not gonna do that here. However, I want to ask every single one of you to please write a comment if you like this material, if you're interested in, for instance, atomics and how to make atomics fast. Maybe I can do another exclusive video on performance of the atomics, a different kind of a data arrangements and whatnot, and different objects, integers, pointers and whatnot. Maybe you want to look at that. And then I'm still planning on doing a longer series, 4 or 5 videos maybe. So I'm still looking for a topic for this. That might be, for instance, high performance custom memory allocators or high performance logger. There's still a suggestion to do coroutines at the assembly level. Yeah, so having a look at those. If you have any other topics that you would like to see, please leave a comment. If you like any of the things that I mentioned as well, do +1, for instance, for custom memory allocators, or +1 for high performance logger. So I know that there's interest there from more people. So which of these topics should I tackle first? And with that, I would like to thank you for watching. Please subscribe, like the video, and obviously leave those comments. And have fun writing fast code. Cheers. Bye.